Alrighty, welcome everyone. Thanks for joining us on this lovely Thursday, week 9. Hope y'all are hanging in there and taking care of yourself and getting some sleep. Today, we're going to talk about some fun topics, and we're going to be trying to think about, can we do better than threads? We've looked at multi-threading safety in terms of avoiding data races, and we kind of looked at, can we do better than mutexes? Today we're going to take more of a performance slant. So we're going to introduce a paradigm called event-driven programming, and event-driven programming itself has nothing to do with safety. Okay, this is really, you would subscribe to this paradigm more for performance reasons than for safety reasons. In fact, if you write your code using this paradigm, it tends to be less safe because it's much harder to write the code in this way. It's harder to understand what's going on. We'll talk about what this is and what everything is. But it's actually a very important technique. It's being used more and more because the performance gains that it offers are becoming more important. They're relevant to particular situations which are becoming more common when you need to have a lot of open connections on a networked server. And we want to have some way to keep the gains of this strategy while also preserving some safety and making the code easy to reason about, avoiding errors. And so that's why we're talking about it in this class. I think it's a very important topic to talk about. If you continue with systems programming, you will encounter event-driven programming, and it might be useful to have in your toolkit some ways of thinking about this that might lead to better and more robust code. So let's start by reviewing threads in the sense of how they are scheduled and how threads are implemented. A thread we commonly refer to as a lightweight process. It's a process in that, it has a train of thought. There's some control associated with it. There's some sequence of functions, some stack running inside of the thread. And there's also associated state. So every thread has, registers for whatever it's currently doing at the moment. It has a stack for what it was doing in the past. So you run some function, return to whatever you were doing before that. It has some status, so on and so forth. And all of this is really managed by the operating system. When you write your code, you just, write sequential code that is do this, then do this, then do this. You implement your code as if it were a sequential train of thought. And then the operating system is responsible for switching between threads really quickly so that you kind of have multiple things progressing at the same time. It creates this illusion that things are running at the same time. And maybe actually if you have multiple cores, then you do have some parallelism. You do have multiple threads actually executing at the exact same time. But you'll always have more threads than you have cores, so the operating system kind of rapidly switches between them so that all threads make some progress. And the way this commonly works is you have a CPU. Let's say we just have one core on the CPU, so it can only do one thing at a time. And we have 5 threads. So 3 of these threads can be doing something at the moment. Maybe they are doing some CPU computation. Maybe they're factoring some numbers. And 2 of these threads are waiting for something external to happen. Maybe they're waiting for a timer. Maybe they're waiting for a child process to exit. Maybe they're waiting to receive some messages on a network socket, but they're waiting for something. The operating system keeps track of what is ready and what is blocked, and it will just rapidly switch between the ready processes. So it'll pull something off of this queue, put it onto the CPU for some time. After it reaches some time slice, after it's run for some amount of time, then it pulls it off the CPU and lets somebody else run. And let's say that we had these 2 sleeping processes over here that were waiting for something to happen. Let's say that the thing that they were waiting for happens. So, I don't know, this thread was waiting to receive a message over the network, and suddenly the message came in. And so it's hey, I can actually do something now. That will get moved to the ready queue. And then the operating system will kind of put that into the rotation of processors that are eligible to actually run on the CPU. Any questions about this? I am assuming people have seen this to some degree in both 110 and 111. All right. So how do we actually, enter this blocking state, or what is blocking? On like we were saying, every thread is going to run for some amount of time before the operating system switches to a different thread, but it doesn't have to run for that full amount of time. Like let's say that a thread gets onto the CPU, and the first thing that it needs to do is like wait for an incoming network connection before it can do anything else. In that case, it will give up its time slice early, because there's really nothing more that it can do that's productive on the CPU at that point in time, right? If the first thing that it needs to do is wait for somebody to connect to the server, well, there's no use staying on the CPU. Might as well give it to somebody else, because there's nothing that we can do. And there's a variety of things that might cause the thread to yield its time slice a little early. And this is generally a good thing, right? It would be a waste if we hogged the rest of the time slice, even if we couldn't do anything with it. Then we're staying on the CPU, we're using resources when some other thread might actually be able to make meaningful progress. So traditionally, we view this as a good thing. We're going to come back to this and re-examine this. It turns out that there are some problems with threads. First of all, there's a context switching cost. Every time you switch between threads, let's say you're running one thread, even if you're switching to a different thread in the same program, there is still some context switching cost, because you are switching the registers, you're switching the stack, especially if you're switching between processes. That's much more of a context switching cost, because you may be like clearing the processor cache. Even if you don't explicitly flush the processor cache, there is still a cache switching cost, because you might have one thread that was in the middle of doing something, then you switch to another thread which might use similar memory addresses, and so it might step on the cache that the first thread was using, and then when you switch back to the first thread, it's whatever it was doing is no longer in cache. These context switches can be expensive. We usually don't think about them as expensive because, well, like I was saying, usually blocking is a good thing. Like this is a huge improvement to whatever we had before. But actually, there is some cost associated with this, and it's something to think about. And particularly if you have servers that are doing lots and lots of things concurrently. Say that you have a server that is trying to manage 1,000 or tens of thousands of connections at the same time. It's trying to talk to tens of thousands of people at the same time. Sure, if one thread gets blocked, there's nothing that you can do for that connection, but maybe you could have taken that same thread and had it go talk to somebody else instead. If you think about this apartment analogy, if you imagine like inviting a bunch of people into your apartment, and you have like people inside of your apartment, maybe employees. Okay, maybe apartment is the wrong analogy here. Maybe it's a store or something. But you have a bunch of people coming into the store, you have some number of employees. Maybe if an employee is talking to one person and then that person is like, hold on, I got to take a call, then maybe it would be productive for that employee to go talk to somebody else, as opposed to just, sitting around waiting for that person to finish their call so that they can resume that conversation. There's also some memory overhead associated with threads. If you have a lot of threads, you consume a lot of memory, right? Every thread has its own stack. A stack is by default 8 megabytes, I believe. And if you're trying to have 5,000 concurrent connections, and you're trying to do this with like one thread per connection, that's going to be 5,000 stack segments, which ends up being 40 gigabytes, which is a very large number. Now, just because you have 8 megabytes of the address space reserved for each thread does not actually mean that you fill all 8 megabytes with stuff. So if you know some things about memory mapping and about how like address translation works, you don't actually have to have 40 gigabytes of memory in use for all of these threads, because it will only use whatever part of the stack you actually end up using. Like you might allocate 8 megabytes for the stack at the very beginning. You might only use 1 megabyte. That means only 1 megabyte of physical memory is actually being used. But I don't believe the operating system will let you spawn more threads than you have memory for, just in case those threads decide, hey, I actually do want to use my full stack. And so this places a bound on how many threads you can actually have. So just to show, kind of what this looks like in practice, let's say you have some program that is, bringing a person into the apartment or into the store or whatever, and then having a conversation with them. This outer for loop is waiting for incoming connections, and then we spawn a thread to talk to that person. This closure function here is having that conversation. So let's say that this thread gets spawned, and it starts running, and it says, finally, the CPU is mine at last. Like, I have some CPU time, I can do some stuff. And what's the first thing that it needs to do? Well, it needs to read from the client. It needs to wait for the client. And this under the hood is making a read syscall, which will block. It might need to wait for a while. So it actually says, wait, I'm actually going to go to sleep. Like, I'm going to yield this processor, somebody else can use it. So it only used like a tiny fraction of its time slice. Right, there is some cost in putting this thread on the CPU. It did almost nothing, and now it's being taken off the CPU for somebody else to come on. And sort of a thought experiment here is, what if we could have reused the same thread to just serve another request while we're waiting for this one? Is there some way that we can reuse this thread to handle multiple connections at the same time? So to kind of give you a high-level summary of where we're going with this, we started out with threads are great. I actually agree with this and believe this, that threads are much easier to use to achieve concurrent programming than processes, just because we have a lot of communication and synchronization primitives that we can use, but unfortunately we can't have too many of them. And context switches can be expensive if you expect that the thread is only using a teeny tiny portion of its time slice. Maybe we would try to look for a way to have concurrency. We still want to have the ability to service lots of people at the same time, but with less penalties. So one thing that you may have heard of in a previous class or maybe in 110, there's a technique called non-blocking I/O. So first of all, do people understand why we have one thread per connection? Or per client that we're talking to? So the reason you commonly have one thread corresponding to one client is because when you're trying to receive information from the client, or even when you're trying to send information to the client, when you're doing read or write syscalls, you have to call read in order to receive whatever the client is sending you. But let's say that the client takes some time to send you some information. Read is a blocking system call. So if you call read to receive whatever the client sent you, that's going to cause your thread to go to sleep for some amount of time until the client actually sends you things. It could be a while, which means that you can't do anything else at the same time. So with what you know so far, you actually really need threads. Like there is no other way to be talking to multiple people at the same time, because within one thread, if you try talking to somebody and you call read to hear like whatever they're saying to you, that's going to put you to sleep. You can't really hear what anyone else is saying at the same time. You can't do something else at the same time. And this is called blocking I/O. So one idea is, well, let's just change read so that instead of going to sleep, if the client hasn't sent you anything yet, it will just return you a special value that says, hey, I know you asked to like receive whatever the client sent to you. There actually isn't anything available right now. The client hasn't gotten back to us yet. So you can go do something else if you want, or come back and try again later, but there's nothing for you right now. And so if you are implementing a thread that is trying to talk to multiple people, you can call read on the first person, and read will come back and say, oh, actually that person hasn't said anything yet. And then you can try to go to the next person, and then so on and so forth, kind of managing many people at the same time. And this allows you to have concurrent I/O with a single thread. Now, by itself, this is not actually terribly useful. You would imagine that, let's say that you have like 1,000 people connected at the same time. It sounds pretty bad if you have to just like loop over 1,000 file descriptors and say like, hey, have you said anything yet? Hey, have you said anything yet? Hey, have you said anything yet? And just over and over. Like, it sounds like you would never sleep. This seems like it defeats the purpose of blocking, which was to go to sleep and get off the CPU when there's nothing productive that we could be doing right now. So maybe that's not so good. But there's another tool in the Linux toolkit called epoll, which you can use, which allows you to go to sleep until at least one file descriptor has something that you can do with it. So instead of like let's say that you're trying to talk to 1,000 people at the same time, instead of constantly checking every one of those people saying, hey, has this person said anything yet? You can just go to sleep and say, hey, epoll, wake me up whenever one of these people says something that I need to respond to. It's kind of like just taking a nap with a bell at the front counter where like if somebody needs some attention, they could just ring the bell and you'll be like, oh, okay, like somebody needs attention, I'm going to go talk to them. So again, it's like say we're a server talking to multiple clients at the same time. Remember, every client is a file descriptor. We can start by asking epoll. We do this in a loop. So over and over again, we say, hey, like put me to sleep, but wake me up when somebody needs attention, and let me know which file descriptor they're at. You know, who is it that needs attention right now? So you kind of go to sleep, and then epoll will wake you up and say, hey, by the way, there is incoming activity on file descriptors 7, 12, and 15. Like you've received new data here, you should go and like call read on it so you can receive that data and then do something productive with it. And you just do this over and over again. This while loop is called an event loop. So you're going to sleep until there are events, until like things have happened that you need to respond to, and epoll tells you about that. And then you go and you handle those events, and you kind of just do this over and over again. Does this sort of like general strategy make sense? Any questions about this so far? Great question. What happens if you have, so with threads, we can use many cores to service a lot of requests at the same time. This seems like we are limiting ourselves to a single core, because here we're having one thread that is managing all these connections at the same time. And this does indeed end up being a problem. So somebody in the chat said, this is it sounds like an advertisement for Node.js, and I don't like it. That's because Node.js actually uses this this model. Like under the hood, this is kind of how Node.js works. And actually, if you know anything about Node.js, it is single-threaded. It's a huge limitation of Node.js applications. You have to do some more gymnastics if you want to be able to use, like to the full extent, a CPU with multiple cores. I actually ran into this week where I've been working on load testing some HTTP servers, actually for Project 2. Trying to improve the infrastructure that lets you evaluate how fast your load balancer is and how scalable it is. Somebody wrote a load tester in Node.js, and I ran it, and it works great, like up until a certain point. And then you look at the like system metrics, and you have one CPU core that's pegged at 100%. Everything else is idle, and you can't improve the performance anymore because, well, it's just not using the other core. So this seems bad. We'll come back to this later on. For now, let's just imagine we're running this on a CPU with only one core. It turns out that once we talk about some more fundamental challenges, we can come back to that, and it's an easy problem to solve. Yeah, any other questions here? This is like an entire lecture in CS 110 in like 5 minutes, so it's pretty reasonable to have some confusion here. All right, so let's get into the weeds a little more, and maybe some more questions will emerge. You might say, okay, you know, I don't know how I would write any code like this, you know, but it sort of makes sense at a high level. Like this seems reasonable. When you actually try putting this into practice, it becomes much messier. And I think the key problem here is that there is some state associated with each conversation. You're not just trying to consume the bytes that all the clients sent you. It's not like you're sitting at a desk in a store and, you know, whenever anyone needs attention, you ring the bell and then you just like listen to whatever they have to say and then go back to sleep. Like you need to actually do something with that, with whatever they told you. You're not just like passively hearing all of the stuff and then like letting that information go into the void. You need to store that state and do something with it. And you can imagine trying to cook 10 dishes at the same time for like a feast or something. If you are a chef trying to manage all these dishes at the same time, you have to remember a bunch of things, like how long has each thing been on the stove? How long have things been in the oven? How long have things been marinating for? What is the next step in each of the recipes? And this translates to actual applications. Like if you're a server, was I waiting for the client to send me something? Or was I actually in the middle of sending something to the client? Write can also block. if you send too much data at one time, you have to pace yourself, and you might have to slow down. So you might be in the middle of sending something, and then the OS says like, "Hey, hold up! Like you're sending too fast. Take a break." And then you have to remember, okay, well, was I actually in the middle of saying something? What was the client asking for before I got distracted? For example, Alice, the client, asked me for her emails, but I needed to go ask Bob, the database, to get those emails. Now, Bob, the database, sent me something, but I don't remember what I was doing before, and I don't remember what I was supposed to do with that, namely send those back to Alice, the client. And managing one connection in one thread is a really easy paradigm for us programmers to deal with, because each conversation is an independent train of thought, and we just write it like that. We're like, do this, then do this, then do this. I've got my variables, I've got my local variables, I've got my stack, like life is good, all the state is there. But if we're trying to manage multiple connections in just one thread, now we kind of have a lot of things jumbled together, and we have to figure out how to cleanly manage the state for all of this. Does this problem make sense? So threads are great. We're trying to find an alternate solution though. Event-driven programming seems promising. It seems like, we can use one thread to do a lot of things. We're going to minimize context switches, and we're going to minimize how many threads we have. But it seems like this state problem is something that we need to figure out. And event-driven programming is not a new idea at all. It's been around since the 70s or 80s. I think somebody linked in the chat a paper to Osterhaus paper on like why threads suck, and he was like a big proponent of event-driven programming. I don't remember what year that paper is from, but it is not a new paper at all. Great, 1995. There you have it. So this is not a new idea. Why doesn't everyone use this? And it's because of this state problem. Like if you want to manage the state yourself, it's actually very, very challenging. We need to develop some paradigms to help us solve this, and this is what we're going to talk about today and on Tuesday. So let's say that you are a chef and you are trying to manage everything. Rust has this idea called a future. And this is not specific to Rust. I'm going to talk about this in the context of Rust and how Rust does things, but on Tuesday I will talk about some other languages, and it's the same idea in many other languages. So a future allows you to keep track of all of your state associated with a particular task, and to kind of like keep tabs on what's happening all in one self-contained package. And you can sort of think of a future as like some helper friend that is kind of overseeing the operation. The executor, the chef now, doesn't need to think about, okay, what is happening with cooking this? What is happening with cooking that? Like, what are all the steps that I need to take? What is the next thing to do? Don't need to think about that. Our executor thread, like what is actually running the stuff, is now going to rely on a bunch of helper friends, which we'll call futures, to sort of remember what is going on and to let this executor know when things need to be done. So you can imagine if you have a bunch of things going on at the same time, let's say we're cooking 3 dishes at the same time, we just have 3 different futures. This executor thread doesn't actually need to manage any state, doesn't need to remember anything of what's going on other than like, okay, I've got my 3 futures here. Each future focuses on the individual task. So this feature might say, hey, we started cooking at 12. This needs to cook for 30 minutes. We started cooking at 12:05. Oh, time's up. I need to like do something with this. Time's up, and they might signal some alarm to the executor saying like, hey, over here, I need some attention. And then the executor can go and do something with the future and like help it out with whatever it needs to do. The features themselves don't actually do anything. So this executor might come to the future and say like, oh, you need to flip this. Okay, I can do that. And then the future will remember, okay, I just flipped this meat. Now I need to cook for 5 more minutes. Same thing over here. And then the executor can go back to sleep because there's nothing else to do right now. Until another feature says, hey, by the way, I need some attention. And then the executor will go over there, give it some attention, do whatever needs to be done. Maybe this dish is finished cooking. So the executor will take that dish and dismiss the feature and say, hey, thanks for your help. We're done here. Go back to sleep until some other features say, hey, attention, I need some help over here. And then the executor goes and like does whatever needs to be done, or if we're completely finished, takes the result, and so on and so forth. Does this basic idea make sense? So how does this actually work in code? Because it's one thing to just have a cute slide animation, but it's another thing to actually understand what is happening under the hood. Features are implemented using a trait, and so you can design any sort of feature. You can make a helper friend that does anything, but it just has to have an interface with a single method called Paul. And I have a slide. Okay, yeah. So the way that Paul works, Paul is a method that is exposed on our feature over here. So this method this feature has a method called Paul, and Paul is where the action happens. That is where you are actually doing things. So the executor thread calls Paul to do something to start it off. For example, maybe this Paul method goes and places this meat on the stove or something. So when the executor thread calls Paul, then that is causing this feature to go and do the thing. Really, it is the thread running that code, right? Because if the implementation of Paul is to place the meat on the stove, and then the executor thread calls Paul, it's the executor thread that is doing the work. It's just the feature that is maintaining all of the state that's associated with this. So this executor thread doesn't need to remember anything. It just walks up to a feature, calls Paul, does whatever work needs to be done until no more progress can be made at the moment. For example, we place it on the stove, now we have to wait for it to cook. And at that point, the executor thread can go back to sleep. So it says Paul, and then we place this on the stove, and then there's nothing more we can do right now. You have to come back later. So what does this Paul method return? It returns an enum that is either ready or pending. So if this task is done, like if the feature is totally done with whatever it was supposed to do, then we return ready with some results. And I'll show this later. But we're not done with this task. If our task was to cook this meat, we just did the first step, right? There's more that we need to do later. There's nothing that we can do right now at this moment in time because we just put it on the stove and it has to cook for a while. But we're going to return pending as a signal to the executor to say, hey, go do something else. I have nothing productive to be doing right now. And it allows this executor thread to go work on another feature, but it indicates that you're going to have to come back to me later. I still have more work to be done in the future. So this executor thread, so the feature returns pending to say, well, I did everything I could right now, but come back later. The executor thread will go do other stuff and eventually will go to sleep because, it will just finish everything that needs to be done at the moment. So this Paul method takes an argument called a context. So when the executor calls Paul on the feature, it is passing the feature a context. And this context has a wake function inside of it. It's a method that the feature can schedule to be executed or invoked whenever progress can be made again. So you can imagine, like, if this feature is going to sleep, if this thread was going to sleep because, there's nothing more to be done here, this feature could set up this wake function in such a way, it could tell the operating system, like, hey, by the way, when this, 5 minutes in the future, in 5 minutes, call this wake function. This is something that is implemented under the hood. I'm not going to get into the nitty gritty of how this function gets scheduled, but somehow the feature says, hey, operating system, invoke this function 5 seconds of the feature. And when that happens, and when this wake function is called inside of this context, the executor thread receives that signal and can figure out which feature called wake, and then it can Paul this feature again. Remember, Paul is where the actual work is happening. This feature has to implement Paul to look at the state and to look at this and say, oh, it's on the stove, it's been cooking for 5 minutes. The next step is to flip the meat. So it might flip the meat and then say, come back later and return pending again. But it's this kind of back and forth where the executor thread calls Paul to do something, feature does as much as it can right now, and then later on when more work can be done again, for example, like a timer elapses or packets come in, some messages come in over the network, or child process exits or something like that, then it schedules wake to be called, which wakes up the executor thread. The executor thread calls Paul again to do more work, and it's this kind of back and forth until things are finished. So 5 more minutes elapse, let's say. We're done cooking. The feature will call wake. Executor thread calls Paul. The feature says, hey, we're finished here. And so now this Paul method, remember I said this is an enum. It can either be pending, meaning that there's more work to be done in the future, but nothing to be done right now. Or it can be ready, meaning that this feature is completely finished. Well, we're done cooking the meat. This feature is completely finished. So this time it's going to return ready with t inside, where t is whatever result type you want to have. In our case, the like end product, the finished product is the meat. And so we can return this back to the executor. The executor is like, yay, I've got this, and I can do whatever I want with it. Any questions about this? I expect this is like a really weird and new concept. What questions do people have? Does the general idea make sense? The executor is still the one that is doing things. It's doing things by calling the poll function, which has the implementation inside. But the key here is that all of the state is encapsulated within each future. The executor thread does not need to remember anything other than what features it's running. The feature keeps track of the task, and the implementation of the poll function, it's specific to whatever task you're doing. So if this is like a cook meat feature, then it's going to implement the poll function to like check, okay, how far along have we gotten, and what do we need to be doing right now? But that's all inside of the feature, so we're kind of self-containing this task to this one little thing. The executor can run many different kinds of features at the same time in order to do many things at the same time concurrently. It's not actually at the same time, so there's no parallelism happening here, right? The executor can only be doing one thing at a time, so it can only be calling poll on one feature at a time. But it's kind of going through them so that they all make progress. If you imagine you're in a kitchen, you take care of this dish, then you go and take care of that dish, and then you take care of that dish, and then you say, okay, there's nothing to do right now, I'm going to take a break. Timer goes off, come back, take care of this dish, go check on another dish, so on and so forth. So, yeah, go ahead, question? This is a really good question, and it's one that I will come back to at the very end. But yes, a very important thing to recognize here is that there are no limits on how long a feature can run. There's no preemption, if you've heard the operating systems term, where you take the feature off the processor if it's run for too long. If this feature has an infinite loop inside of poll, that is going to stall everything. Right? This executor is going to call poll on this feature, get stuck inside of this feature's poll infinite loop, and won't have a chance to go to any other features. And this is a bad thing. It's something to be aware of. But I will come back to that on the last slide. Any other questions? So I've been talking about this trait, and you imagine that this is this little octopus here, or our feature helper, is kind of like a type that implements this trait. You might be trying to think in terms of code, like, okay, well, how do I actually implement one of these things? It turns out that pretty much no one actually implements features themselves. You will never implement that feature trait on any of your own types unless you're working on a very low-level library. It turns out that some low-level library implementers implement a set of basic features, and everyone builds on top of that. It's kind of like the saying, like, it's turtles all the way down. Well, in this case, it's features all the way down. You can combine features with various combinators, and let's say that you have a set of features already implemented. Let's say that we already have a place on stove feature, we already have a cook one side feature, we already have a flip feature, and then we already have another cook on, or the same thing. So we have 3 features here. We can combine them to make our cook meat feature. So we can say, hey, let's assume that we have some raw meat. First, place it on the stove, then cook one side. Then once that feature is finished running, execute this other feature, flip feature, do this. And then once that is done, then do this other thing. And these combinators allow you to string together existing features to create new features. And what this looks like in practice is, let's say that we're halfway through. Okay, so we have already cooked one side, it's time to flip. We have this big feature right here, this feature that I said let feature equals, that's this guy, which is implemented in terms of these 4 smaller features. So when the executor thread calls poll, the implementation of this feature with all of these .thens, this is implemented for you, right? You don't actually have to implement this yourself. But the implementation of this is such that it remembers which step that it's currently on. And it says, hey, we've already gotten past these first 2 features. So the next thing that I need to do is this 3rd feature here, flip feature. So I'm going to call poll on our flip feature here. And then likewise, when this flip feature calls wake on that context, it's going to be part of the same context of this feature. So that is going to, you can imagine it's like poking this feature, which then pokes this executor thread saying, hey, wake up, there's something to do. This executor thread will call Paul. This feature will remember, okay, we've gotten through this one now, and then it will call Paul on this last feature here. Does that make sense? It's a chain of features, and we're just stringing them together. And not only can you string them together sequentially, so in this case, we said, do this, then do this, then do this, then do this. You can also string them together in other ways, including in parallel. It actually turns out that in some ways it's easier to have parallelism using, or not true parallelism because it's not running at the same time. It's easier to have concurrency using this model to do several things at the same time than it is maybe using threads. So for example, we can submit, well, I'll come back to that bullet point. That's actually maybe not so relevant, but you can write features that depend on multiple concurrently executing features. So you can say cook meal feature. Like if you want to cook a whole, 4-course meal, then you can put a bunch of sub features that will all execute at the same time. And then this large feature here, this cook meal feature, will keep track of, okay, what has finished so far and what still needs to be polled, what still needs to make progress. And let's say that the first 2 features have already completed. So they've already returned ready, saying, hey, I'm done, here's the end result. This feature will just remember that, like, okay, these 2 are done. And when the executor thread calls Paul, then this feature will go and say, okay, these 2 haven't finished yet. I'm going to call cooksoup.paul and then bakebread.paul. Remember, there's no parallelism. It's not actually doing things at the same time, but it's concurrency in that, it's making whatever progress we can on cook soup right now, and then walking over to the bread and making progress on whatever we can with that, and then going to sleep. And then whenever something else can make progress, we get that wake, which is going to wake up the executor thread. The executor thread asks this feature, like, hey, direct me, point me where to go right now. And this feature will say, okay, this dish hasn't finished. Like, let's go poll that. Let's go work on that. Does that make sense? Yes, a multi-core processor can do this in parallel, and I'll show that at the end. But let's just think single core for now, for simplicity. I agree. I think future is not a, like, it doesn't really capture the idea behind this. So first of all, the reason that they called it the future is because it stores some like results. I'm going to butcher this. You should actually look it up for the precise explanation. But it's because it like stores some operation where you can get the result in the future. It's like some in progress thing that may or may not have finished. In writing these slides, I was trying to think about, is there a better name that we can use that like captures the idea behind it more? And I'm not really sure. It's such a different and weird concept from everything that we've seen in the past that I just drew it as like a purple blob. It's like this helper thing that is managing your state, but it's not actually doing anything, right? Like in a thread manages state and it also takes care of execution. You write your code inside of the thread and it's executing inside of the thread. With a feature, you're storing state and like defining the behavior to execute, but a feature itself is not ever like executing on its own. It only does stuff when an executor thread calls Paul, and is the implementation of this Paul function that actually does work. So the feature itself is not really doing work. It's the executor thread that's doing work. It's the feature that is directing it what to do. It's kind of a weird idea, and I couldn't think of like a single word that kind of captures the essence of it. If you're familiar with JavaScript has something called a promise, which is basically the same thing as a feature. And I don't know why they called it promises. Maybe it's like because, in the future, I promise you that like I will return you this result. Maybe, I don't know. It would be cool to look up the etymology of this and see how they came up with this. But yeah, for better or worse, it's the same idea. Yes. So task is, it's a great word. Everyone knows what that means. It's something to do. right? The problem with the word task is that like everything's a task. It's a very general, broad term. Like a thread is a task too. It's just like, something to do. So it's not specific enough to capture this particular mechanism that we're talking about. Okay, somebody just posted in the chat. The term promise was proposed in 1976. Wow. I'm telling you, these are not new ideas. And Peter Hibbard called it an eventual. A somewhat similar concept, future, was introduced in 1977 in a paper by Henry Baker and Carl Hewitt. So it's just a bunch of academics like coming up with stuff, and we use the names now. Yeah, it's an excellent question. If this is such a good idea, why did it take so long for this to emerge? I think there are several reasons, and I'm like by no means an expert in programming languages or in the history of programming languages, so take my explanation with a grain of salt. And there are going to be more reasons than what I say. Part of it is like efficiency. So we're going to talk about how you actually write programs with these things on next Tuesday. It turns out that you don't usually... Okay, this you might occasionally write. Nobody writes code like this. This is not something that you would usually find in Rust code. And we'll talk about how you actually do it and how that is being compiled under the hood. But it turns out that it's actually very difficult to implement a compiler that uses these things in the way that we want, which we'll talk more on Tuesday. And the compiler has to do some pretty sophisticated analysis on the code. Or if it doesn't do some sophisticated analysis on the code, so take JavaScript, for example. There's like no, I shouldn't say there's no sophisticated analysis. That's totally false. Like the V8 runtime or whatever VM that you're using, it does do a lot of analysis on the code to try to help improve the performance. But there's no analysis in terms of like, I'll talk about what analysis they're doing on Tuesday, and then it may make more sense. But the compiler is not doing anything sophisticated for promises in JavaScript. Instead, what it's doing is a lot of dynamic memory allocation, where if you have some problem that is composed of a bunch of other futures or promises, and it's turtles all the way down, every one of these ends up doing dynamic memory allocation. And there is a lot of indirection in that you call Paul on this, which calls Paul on that. In Rust, all of this ends up getting compiled down much more efficiently, and there's much less dynamic memory allocation. And so the performance of this is matching what you would expect if you wrote this like event-driven code that I showed at the very beginning of this with like epoll, and you're like managing all of the state yourself. If you did that in C++ or in C, you would get the same or comparable performance as if you used futures in Rust. And that is a huge technological accomplishment that hasn't really been a thing in the past. And so with JavaScript has had promises for a long time, but it achieves it at much higher cost to performance. So hopefully that helps give you some answer. I can go into it more on Tuesday. But one thing that's kind of crazy about this is like if you can have these primitives and then you can combine them together with these combinators, you can actually write. Where is the slide? Okay. You can actually write your entire program as one huge feature, right? Like if you have a main function, your main function is going to do something and then do some other thing and then do some other thing, and maybe do some things concurrently, like make sure all of them are done, then do some more stuff. And you like if this is a feature, you can combine this. You can say like do this and then do some other stuff, and then maybe do some more stuff concurrently, and your whole program can turn into one huge feature at the very top level. And I will show you how this actually happens with some extra syntax. Again, I mentioned like the syntax, it's not bad. You could certainly write programs like this, but it's also a bit different from what we're used to. And there is some other syntax. You may have heard of async await in other languages, which is what we'll talk about on Tuesday, which kind of bridges the gap and allows you to write code that looks almost exactly like what you're used to already, but under the hood gets compiled down into these features and sub-features and stuff like that. And if you think back to the original problem that we were trying to solve this problem of like using a single thread to do many things concurrently without having a mess of states to keep track of. And this kind of solves that problem because each feature has a self-contained state. It knows what is happening, what the next step is. It knows what we're supposed to do. And it's self-contained in that, we might have a feature for cooking meat, we might have a feature for cooking soup. So we avoid all these messy state management issues that are commonly associated with event-driven programming. Again, event-driven programming is not new. It's been used for 20 years in like production servers, and it's been around as an idea and in like more experimental contexts for a lot longer. But this allows us to make it a lot easier to control the state and not have a big mess of spaghetti. So just as a recap, event-driven programming is nice in theory. We had this problem of managing state. Features help us to encapsulate that state for in-progress operations, making this cleaner and more practical. Any questions about the stuff that I mentioned? So I've talked a lot about the features themselves, as like thinking about them as tasks or as operations. Let's talk a little bit about the executor. Now, because features define the thing that you need to do, because the task is defined inside of a feature, it turns out that you will never need to write code for an executor, because the executor is general. You just like submit features and you're like, hey, can you do this task? Can you do this feature? And the executor, all it needs is like a single poll method on this feature. It's fully general. And so there are a bunch of off-the-shelf executors that you can just use in Rust. And you just submit features to them, and they just go and call poll on your features, and your poll methods do all this stuff. But how do these actually work? It's helpful to know because this influences the design decisions that you make when you're writing feature-based code. So an executor is just looping over the features that can make progress at the moment. It's the event loop. It's the thing that we showed at the very beginning that says like, while true, see what can be done and like do the things. It's basically what's going on here. If there are no features that can make progress, then the executor still goes to sleep. So we're not wasting CPU time here. But as soon as one of the features calls wake, then this executor wakes back up and does the thing. It goes through the features and polls them. Like I mentioned, there are lots of different executors and they're fully general. You don't have to implement one yourself. The most common one by far is called Tokyo, and you can, so we made the last milestone optional. The last milestone is where you use this. I would, if you have the time, or maybe even after the quarter, I would recommend checking this out because like I mentioned, this paradigm of event-driven programming with promises or tasks or Go routines, or many different languages are adopting this. C++20 actually just got coroutines, which is the same thing that we'll talk about on Tuesday. So you're going to see this much more as you go into systems programming, and it will give you a massive performance speed up on your server. So it'll be fun to check out, but you don't have to do this milestone. And so if you do that, Tokyo is the one that you'll be using. And so this is the answer to the question about can we do things actually in parallel? Tokyo is implemented such that if you have several features that you want to be doing at the same time, it can schedule those features and call poll on them from multiple threads assigned to multiple cores. So let's say that you're running on an 8-core machine. At startup, Tokyo will spawn 8 executor threads, and then it just has a pool of features that need to make progress. And whenever you have some features that need to make progress, one of those executor threads will raise his hand and say like, hey, I can do that. And it will call poll on that feature so that, it will go do that thing. That way, if you have multiple features that could be run at the same time, you can actually be running them at the exact same time in parallel. This is different from Node.js for a couple of reasons, where Node.js only has one executor thread. With Rust and Tokyo, you can do this with many. It does mean that you have to protect shared data using synchronization primitives. This is why you don't really see like mutexes in Node.js. But Rust forces you to do that anyways with the ownership model. And so that's not anything new. So if, this is kind of the state diagram for a feature where you spawn a feature, you call poll says like, hey, there's more stuff to be done in the future, but I can't do anything right now. So it returns pending to say, I can't do anything. Eventually it calls wake. Then the executor calls Paul. Eventually Paul will return ready saying that we're done. And I mentioned that the executor thread is kind of going through this in a loop, in this event loop, where it's got a bunch of features, just goes through the features that can make progress, calls Paul on all of them. What happens if you call Paul on a feature and that leads that thread to go to sleep? Like, what if you had a wait PID in there? Or what if you had an actual sleep call in there? Or something like that? What's going to happen to the program? So not necessarily deadlock. It's not necessarily deadlock. Let's just say that we have an executor thread calls Paul on our feature, and the Paul implementation calls sleep. Exactly. So the OS will put the executor thread to sleep, which means that the executor thread can't go and make progress on other features because it's now asleep and like stuck on this feature, which is not great. Or if you called like a blocking read and there was no data available, that's also going to put you to sleep. And now the executor thread is no longer doing things concurrently, is tied up on this feature, which is bad. So when you're writing code that uses features, you have to, you're not going to implement the executor, but you have to be thinking about what it's doing and keeping that in the back of your head. If you write some blocking code inside of a feature, then that is going to cause the executor to go to sleep and is not going to be able to continue to other features, and that basically defeats the purpose of what we're doing here. And what that means is that you have to use non-blocking versions of everything. Non-blocking version meaning that it causes Paul to return pending, saying like, hey, I can't do anything right now, I'm waiting for something, come back later. And then when that thing is done, it schedules wake to be run when that's finished. So you have to use a different sleep function, all right? You don't want to actually go to sleep. You just want to return pending saying, hey, I'm waiting for a timer. There's nothing for you to do right now. And then when that sleep is done, it will call wake. You need to use a non-blocking mutex that says, hey, I'm waiting for this mutex. There's nothing for me to do right now. Like, go do something else. And then when that's done, like when that mutex gets unlocked, then I'll call wake. Any system call that would normally block, you have to use a different version. And this seems like kind of a pain. It kind of is. And you'll see this in the assignment. If you work on this, you actually have to go through and like find all your blocking calls and convert them to non-blocking versions. I think honestly, this is like the biggest sticking point of this design right now. This is not unique to Rust. This is a problem with like all languages that use this sort of design. But it is like something that's very important to be aware of. Executor runtimes like Tokyo provide, like they basically have a second standard library. So instead of doing like standard sync mutex, you do Tokyo sync mutex, and those are the implementations you have to use. So something to be aware of. It is definitely a problem with this, and maybe in the next few years somebody will come up with a clever solution. That would be amazing to see. So on, actually this should say Tuesday. On Tuesday, we'll talk about some new syntax for making programming with features even easier. Here are a bunch of links if you're interested on like the design battles between threads versus events, and like the emergence of features and promises and all of this stuff. There's a bunch of really interesting talks and blog posts here if you're interested. But that's all I have for today. Stick around if you have questions, and I will see you on Tuesday. Have an excellent weekend. Hang in there, almost there, 1 week left, and we will be done. So see you on Tuesday. There's a question in the chat. Will the compiler warn you if you have some kind of blocking in the future? No, it will not. And this is like very sad to me. It is actually a very difficult problem because the compiler doesn't necessarily know which functions will block. And even worse, it doesn't know which functions will call which functions. So let's say that you have some function that blocks. If you have a helper function that calls that function, the compiler needs to realize that now that helper function can also potentially block. And that link is not always clear. I think in Rust it might be a little bit more tractable for the compiler to establish this because Rust has restrictions on like what you can and can't do and can and can't call, but it's still difficult. And so yeah, it will not warn you. It's a big problem. You have to be careful. It's an even bigger problem in other languages. I feel like there could be some tools that could be developed for Rust that will warn you because Rust has a compiler that is already doing a good amount of static analysis. And other languages like JavaScript, you're in trouble. Like there's no good way to do this, and this is a big problem in JavaScript as well. Question: so you could actually get away with mutexes if you used try lock or timed locks. So try lock is a non-blocking mutex lock call where you go and you acquire it if it is unlocked, or if it is locked, then it just returns an error saying like, hey, the mutex is locked. That is totally fine. You could do that. How useful would it actually be though, right? Like eventually, like assuming that you do eventually want to acquire the lock, you're going to have to wait for it. And so you're either going to be spinning and like busy waiting, or if you want to get pulled off the CPU, you're not actually getting pulled off the CPU. But if you want to yield and tell the executor thread to go do something else, then you might as well use like the normal version. But yes, that would be fine. Timed locks, I'm not familiar with. Is that like a lock with a certain timeout where it will just return after a particular amount of time if you don't acquire the lock in that time? Yeah, so for the particular amount of time that you're waiting to acquire the lock, it would still be a good idea for the executor thread to be going and doing something else. I think Tokio has async versions of timed locks that will, for that sleeping duration, will go do something else. The impact is not quite as bad as a mutex, but still, it would not be great to call that from this asynchronous code. Any other? Yeah, what's up? Excellent question. So features are part of, I don't know if the feature trait is a part of the core language, but they're kind of part of the design of Rust. But there are many different design decisions that you could make in how to implement this. Features a very, very simple interface, and you could do anything you want with that. And other people might want to create executors that do different things. For example, maybe you want to like set a priority on certain tasks to do those things more importantly, or you want to implement some like fancy things with like priority donation or anything. Essentially the executor is re-implementing a lot of logic of the operating system scheduler. And if you think about how complex scheduling is, there's a lot of different design decisions that you could make there. And so the designers of Rust do this a lot. When there's contention, just like ship the bare minimum, like the thing that everyone agrees on, let other people do things the way that they want. And that's kind of what they did here is they shipped the interface, the design, and it's up to you if you want to implement your own executor or your own features, or you can do whatever you want with it. So Rust Standard Library does not have an executor, which is why you have to choose one. And Tokio is like by far the most popular one. It's a very, very popular library. That's right. POLL? Well, I don't think it stands for anything. I think like to Paul is just to check. I don't know. Maybe this is like a Midwestern thing. I just say Paul, and other people say Paul. Yeah, I think that's just my accent. Yeah. But I don't think it stands for anything. Like, it's not. Polling has a particular meaning in computer science in that it's like to like periodically check on things, and sometimes it's a bad thing. So say you're looking to check if something has happened. Maybe you're looking to check if you've gotten a new email. Sometimes there are like two trains of thoughts where you can either poll to see if something has happened, or you can like get an alert. Like you can either repeatedly check your email, or you can just wait for a notification. And this is like a common design decision in many different areas of computer science. This is a little bit different, right? This kind of polling is not checking to see if something has happened. We do have a mechanism for that with the wake. This poll is to just like periodically come in and do something, and then maybe we have to wait some more. So then later on we come back and we do something. Maybe that's a little confusing terminology. I'm not sure how they decided to pick that. But yeah, that's what we got.